So here's the plot in your homework assignment. And this is from Stallings' book on wireless. Stallings is a great computer science author. I'll tell you if you have any of his books. This is a great plot. What we're seeing here, and I'll use the little pointer, is that we have loss versus distance. Okay, so this is free space loss. This is not terrestrial loss. This is not loss in a city environment on the surface of the earth. This is not the loss out in the countryside with light forestation and buildings and hills and valleys. This is not loss inside a large office complex or inside a big factory. This is loss out in space. And so basically applies to satellite systems. And we do have models, and you will see that I show you the mathematics of this equation, and you'll have to take that and apply it. This represents an inverse square law. Okay? This is the inverse square law, and you can see that because for every 1 decade in the horizontal, notice the horizontal axis is a log axis. Are you guys familiar with that concept? Okay, in any case, instead of having equal additive increments along the horizontal direction, we have equal multiplicative increments along the horizontal direction. And the vertical axis is in decibels. It's not labeled as a log axis. It's labeled linearly, but by virtue of putting our loss ratios into the units of decibels, it is also a log axis. Okay? And you can measure the slope of a straight line. So when you have a log-log plot like this is essentially a log-log plot of loss. What you're going to see is that a power law, that is y equals x to some power, will yield a straight line. Okay? Because if you take, let me just show you real quick. If you have y as a function of x is equal to x to the alpha power, if I take the log of both sides of that, log of x to a power is alpha log x. So if I plot, let's call the log of y big Y and the log of x big X. Here I have big Y versus big X is just straight line with slope alpha. Okay, so this is the basics of a log-log plot. In any case, though, we have straight lines here, so we do have a power law, and the alpha is technically -2 because it's an inverse square law. However, we have a minus sign in our definition of loss, so it now has a positive slope. And you can tell that the slope is 2 because for every 1 decade along the horizontal axis, we have 2 decades along the vertical axis. And you can see that right here. You can see that in going from 1 to 10, we go from just over 60 up to just over 80. So you can see the slope of 2 right here. This is the inverse square law. When we get to a terrestrial loss model, and there are lots of these things, if you go on Wikipedia, you can find the Hatta model and the, I'd have to think for a moment, all the names of these things. But basically what we do is we assign a different exponent. And so we may have an exponent which gives us less loss for distance with an exponent less than 2. Like if you want to measure loss down the hallway, you might get an exponent of less than 2 because it's bouncing off the walls and sort of concentrating. It's not spreading out as much. If you want to measure the loss in an urban environment, you might have an exponent greater than 2 because it sort of spreads out and bounces all over the place, causing some partial destructive interference. So we see these straight lines, and we also see that as we go to 10 times the frequency, each line up is 10 times the frequency of the lower one, we have an increase of just exactly 20 dB of loss from 60, what is it, about 63 to 83, 103, 123, 143, etc. Okay? That's pretty neat. So we have that rule, a simple rule that says you multiply the frequency by 10 and you get 20 dB more loss. The other rule we have is very similar, is if you multiply the distance by 10, how much does the loss go up? Can you guys see on here? So if I go on the lower line, if I go to 1 kilometer and then the 10 kilometers, how much has the loss increased?
Almost 20. A little more than 20.
It's actually right on 20. See that line there? We can see right straight across there. It's also the same rule. You multiply either the frequency or the distance by 10, and you've increased the loss by 20. Similarly, if you divide the distance or divide the frequency by 10, you decrease the loss by 20. Two very simple rules to remember. Okay? Here's another even cooler thing. This is at 30 megahertz, 300 megahertz. Here's 3 gigahertz. This is pretty close to our 2.4 gigahertz, right? If we plug in 2.4 in this plot, guess where it lands at 1 kilometer? Right smack on 100, 100.0. And so we also have, we have those two easy rules to remember. We also have that the loss at 2.4 gigahertz at a distance of 1 kilometer is 100.0 dB. It's a real nice coincidence. And so if we want to go to 100 kilometers, 1/10 that, how much is the loss? We have this rule.
10.
It would be 1/10 the distance, right?
Yeah.
Yep, 100 meters is 1/10 the distance. And if I multiply the distance by 10, it goes up by how many dB? 20. And if I divide by 10, it goes down by, and so it goes to 80. And if I want to go to 100 meters, now I want to go to 10 meters. How much loss?
20.
20 down again, 60. Right. So 10 meters, 60 dB loss. 1 meter, 40 dB loss. 1 meter is not very far, and in free space we have 40 decibels of loss. 40 decibels of loss represents only 1/10,000th of the signal coming through in milliwatts. 10 to the minus 4 is 40 dB of loss. Okay? In any case, this is the fundamental of this free space loss equation, and I think, do I even give it on this sheet? No, I give it in the other video, and I show you how to derive it. And one of your homeworks coming up will be to reproduce that derivation in the other video with a different exponent. Okay, so I'm going to ask you to do that in a homework. So I do want you to understand that mathematical video that I posted. Yeah, Jeff.
That diagram represents any radio wave in free space.
Yep, radio waves of different frequencies. Yep.
So would that be different? Is that like in air?
This is in free space. Air is about the same. Yeah, yeah. This is free space without an atmosphere. The atmosphere adds a little bit of loss, but not much. It's not appreciable, really, unless it's raining and snowing. And if you have dish TV, you know that if it starts snowing and really raining hard, you might lose your signal. Yeah. This is like a clear atmosphere without lots of fog or rain or snow. Okay, so this is just a quick primer on your homework. Does this make sense, basically? Okay, I hope so.